In Learning Objective 3, we start a new chapter called Instructions, Language of the Computer. This is relatively a long chapter introducing the language of the computer. We will learn a new programming language that is very close to the language of machine. And this learning objective kicks off by overviewing operations of the computer hardware. To command a computer's hardware, you must speak its language. The words of a computer's language are called instructions, and its vocabulary is called an instruction set. We take a top-down approach to understand the machine language. We will learn how to translate high-level languages like C down to bit strings, zeros and one, that could be understood by hardware. Instruction sets are pretty long documents explaining operations supported by the hardware. They are usually open source and you can find them online. Here are some example instruction sets for you to look up. ARM v7 is the instruction set used by processors of almost all smartphones. Intel x86-64 is the instruction set used by desktop and laptop and supercomputers. MIPS is the instruction set used by network processors for filtering the network traffic. In this course, we learn MIPS as a representative of instruction sets, and we learn how to communicate with hardware using MIPS syntax. Goal of designing an instruction set can be various things. For example, it can be finding a language that makes it easy to build hardware and a compiler, and with the goal of maximizing performance and minimizing cost and the energy. In this chapter, we are introducing an example instruction set, which is MIPS. We learn how instruction set is represented in the hardware. We learn format of the instruction set in the hardware as well. We learn the relationship between instruction set and high-level programming models, and we get to know how compiler converts from high-level to low-level instruction sets architecture. We see the impact of programming language and compiler on performance, and we learned the concept of stored program. The language we are going to learn here is called MIPS assembly. This and next slide list all instructions we are going to learn in this chapter. Here you see arithmetic and data transfer instructions. Instruction column lists instruction names. Example column shows the syntax of the instructions. Meaning column shows the C-like equivalent of the instruction. And comment column explains the instruction. For example, we have add instruction at the first line. Add takes 3 operands and performs add operation on 2 operands and store the results in the 3rd operand. Second row, subtract instruction does pretty much the same thing, but instead of adding, it performs subtract. Data transfer section are used for moving data between arrays and variables. We'll have one whole learning objective to discuss about data transfer instruction. This is just to show you what is coming up next. The second sheet is the list of 3 more categories of the instructions. We have logical operations, conditional branches, and unconditional branches. And logical operations are like add and subtract, but they perform logical operations. They perform and, or, nor, and shift right and shift left. Branch instructions are used to implement if-else, for loop, while loop, switch case, and all forms of control flow statements that you can think of, and you can use in high-level programming languages. We have one full learning objective to discuss branch instructions. Now that we have a big picture of where we are going in the next few learning objectives, let's focus on understanding MIPS assembly language first. Every instruction in MIPS assembly language is one single line. It is made of one operation and has 0 or more operands. Operation is the action performed by the instruction, and operands are inputs and outputs. For example, in the instruction shown in here, add is the operation, and A, B, C, R are the operands. In assembly, new line character determines the end of the instruction, like semicolon we have in C and C++. Operands in MIPS assembly can be registers, memory, and constants. The size of every register is 4 bytes, equal to the size of integer variables in C and C++. We refer to 4 bytes simply as one word sometime. MIPS assembly has total of 32 registers. 32 4 bytes gives us total of 128 bytes for entire registers. Registers have particular names as listed in the table here. For example, we have S0, S1, S2, all the way to S7, T0, T1, T2, all the way to T9, 0, A0, A1, so on and so forth, for a total of 32 registers listed here. Beside registers, we can also use memory words as operands. MIPS support up to 2 to power 30 words. Every word is 4 bytes, like we mentioned. So entire space of memory is 2 to power 32 bytes. We use data transfer instructions for moving data between registers and memory and reverse. For practicing MIPS instruction set, we use an online tool called VMIPS. Check the link here, paste any code we show in learning objectives and practice in the tool and get to know how the tool works. The number of assembly instructions are very low because they need to have one-to-one correspondence in the hardware. Assembly instructions are also rigid for the very same reason, because they need to have one-to-one correspondence in the hardware. By rigid, we mean the number of operands are fixed. Operations are fixed, and new operation operands cannot be introduced. For example, we cannot add 4 numbers at the same time in MIPS. High-level programming models are very flexible and can be written in various styles. Assembly and instruction set are carefully designed to be able to support that by breaking high-level instructions down in a way that can be developed by assembly language and accordingly be executed by the hardware. In this chapter, we learn this careful design, and we get to know how complex high-level instructions can possibly break down into very simple low-level assembly sequence. For example, adding 4 numbers in assembly is done by adding 2 numbers at a time and accumulating the result in a partial sum. In MIPS syntax, every line takes maximum of 1 instruction. Line or instruction terminates by new line character. For example, the given one-line CS statement is translated to MIPS and ends up to 3 assembly instructions, hence 3 lines of code. In this chapter, we learn about design a lot, and we learn 3 design principles that are kind of general guidelines in every designing problems. Number 1 we can introduce here is called simplicity favors regularity. Meaning that aiming for having a very regular design with less exceptions simplifies the implementation a lot at the next step. For example, MIPS limits all operations to have maximum of 3 operands. We don't have any instruction in MIPS that takes 4 operands. As we'll see later, this limitation, this regularity will simplify the complexity of the hardware a lot. Let's see the first example. We have this C code sequence, and we want to translate this sequence to language of MIPS assembly. What we see in here, we see two assignments. They are dependent. So result of A is result of first instruction is using the second instruction. We always translate the instructions from high level to low level with the specific order given in the sequence. So let's translate the first instruction, then we go for the second instruction. So if you want to translate the first instruction, we see one add operation. So we add the add operation. Destination of add operation according to the syntax is the first operand. So destination where the result of add will be stored should be A, and the operands of add are B and C. The second operation is a subtract, and the result of subtract should be the first operand of the instruction based on the syntax, and that should be D. So the result of subtract will be stored in variable D. And then we have variable A to be subtracted by E. So that's the code sequence we'll end up with in assembly of MIPS. Let's see another example. Another example we have in here is a little bit more complex operation. Two add operations, one in here, and one subtract operation. Basically have 4 operands and 3 operations to perform. We have to break this down into simple instructions that are understandable by MIPS. We can do add or subtract 2 operands at the same time. So I can simplify this by writing it down into the following sequence. So it can be equal to F equal to G plus H, and then F equal to F minus I, and then F equal to F minus J. These 3 instructions perfectly can be translated to MIPS assembly and correspond to 3 instructions there. So let's convert them and compile them to MIPS assembly. So we add them. F will be the location we store the result. First operand G, second operand H. The second instruction is subtract. First operand is the destination where it is F, and first input will be F and will be subtracted by I. The next instruction is also another subtract, and destination is again F, first operand F, and the final result and the second operand is J.